time as an architectural student, actually. So we visited Sao Paulo, Rio de Janeiro, Brasilia. It's wonderful to be back from another perspective now. And I'm very excited to continue working here together with the university. Thank you also for the great talk before. A lot of the topics that were addressed by Wanderlei will be part of my talk as well. And so there's no surprise that the title is also very similar. It's called Sustainable Construction with Digital Fabrication. So can you hear me? I would like to start with a quote from Ludwig Mies van der Rohe. He said, he defined architecture as, architecture starts when you carefully put two bricks together. There it begins. And I think, and our perspective on this minimal definition of architecture is, in regards of information technology and digital technology, we can rethink all the components of this sentence. So we can rethink what will be the future bricks in architecture. We can think about who will put them together. Maybe it will be robots on the construction side. But last but not least, very importantly, what does it mean to plan or to design carefully, and how can we use the computer also to design more carefully in our times? To give you a little bit background of the motivation of our research, as an architect, I'm always surprised by these numbers. So construction industry is really one of the biggest industries worldwide in terms of impact and also economical importance, especially in terms of material consumption. Construction industry itself is already responsible for 30% of the material consumption, roughly. And within the material consumption, cement plays a very important role, is also responsible in the production for CO2 emissions. So these numbers show a little bit how relevant it is to make research in this field. On the other side, if we look at the future perspective, considering the ongoing global urbanization and the increasing demand of housing, this becomes even more dramatic. So in the last 100 years in US, there was as much concrete used than in the last 3 years in China. And these numbers are still increasing. On the flip side, so these are the global trends and tendencies. On the flip side, if we compare how construction evolved over the last 100 years, on the left you see the construction of the ETH Centrum University from Gottfried Semper, the architect, designed. On the right side, one of the highest buildings in Switzerland, actually. Would be here a very small building, Prime Tower. But if you compare the images closely, it's still almost the same. People are standing with wet shoes in concrete. Not everybody is working usually on the construction site. And maybe the only difference is that some people are now wearing helmets. So, but this has a serious impact also. So if you look at the productivity of construction industry and compare it to other manufacturing industries, for example, car industry, the productivity did not increase in the last 30 years. And that is more or less the time where also the first digitalization kicked in other industries. This is an abstract number, but to make it, to explain it a little bit, the impact means that housing didn't become more affordable for people. So we still have to work as much to earn or to be able to afford a house than 30 years ago. And this has to change also. On the same time, one can say that digitization will come in construction industry, definitely, but it's not there yet. So this was a survey from 2015, and it shows that between different disciplines in construction, we are just right now on top of agriculture and hunting in terms of degree of digitization. Of course, agriculture is already very much digitized in the last year, so maybe we are now on the last spot. So there are central aspects of our research, the framing our research. We will have more and more technological integration into buildings, so we have to find the right way to do that also. In order to answer the increasing demand of housing, we need to increase the amount of prefabrication and modular construction. This doesn't mean that we should build standard houses, but we still have to think in prefabrication. And of course, we have to put an additional focus on sustainability, and it will automatically also come together with rising material costs that we need to be prepared for. And as it was already mentioned before, smarter design software, BIM, will become more and more relevant. And I would like to now show you a little bit the research that we do in the field of digital fabrication and computational design, and but more the experimental research work, and then go into detail into a house that we built together with colleagues, the DFAB house, to show you what impact it can have. So that is the scope of our research. We call it the digital process chain. So we seek for processes that start digitally in the computer as a design and stay digital until the end of construction. One part of it is, of course, digital fabrication. And one very simple, naive question could be, can robots build better houses? If you look at car industry, and that is part of the increase of productivity there, is it's already very much automated. Huh? But these machines are more smart than just building always the same cars. So they could also potentially build very individual houses. And Vanderlei already showed the robotic fabrication lab. That is why we have this infrastructure to test how robots could build buildings in future. And here the special setup for us is also a large 3D printer, because it actually has 40 meters by 12 meters print box size. But it is 4 robots can also work together. They can work together for complex tasks. So if you want to handle complex geometry, but they can also work together with humans next to each other. So that's a very important aspect. That it's not that robots will completely remove humans on the construction site, but people will work next to robots. But more important for our research, and I think this is also important for the entire discipline, is that we work in interdisciplinary teams. So Switzerland started this national research initiative called NCCR Digital Fabrication, which brings together researchers from various kinds of disciplines. For example, I'm an architect. I'm part of this team, principal investigator, together with structural engineers, material scientists, roboticists, computer scientists. Together with 50 PhD researchers, we try to develop a new digital building culture. And we strongly believe that only in a interdisciplinary team, we heard before, it's probably combining existing things, then we can have a big impact. To show you, so we started with this research 4 or 5 years ago. I can give you maybe an overview of the last 4 years, where you see the scope not only of our research group, but of the entire discipline, the entire initiative. As I mentioned, you see robots working together. I will go a bit more into detail later on part of these projects. Robot doesn't mean that it is an arm. It can also be a 3D printer. You will later see it can also be an excavator or a knitting machine. As you can also see, there's still a lot of manual work in parallel to the automated work. In the background you saw our institute as well. It's about how can robots, for example, orientate on the construction site. That is one of the big questions. How can they work on an uncontrolled environment outside of the factory? In this example. This big space is not only a robotic fabrication laboratory, but we use it also for one-to-one tests. For example, Philip Block's group built a large thin shell structure, one-to-one test of the future test house. So every of these research projects that you see here is always made of teams of at least 3 to 4 different disciplines. 3-year-long research streams based on a deep collaboration between different researchers. We also teach younger students, master students, postgraduate students. We test extensively. Yeah, and here you saw the team. So our part in this big research group is has a focus on 3D printing. And for us, the first 3D printer is this kind of weaving machine, the loom. That was already a machine that could program by computer, by code, long before there was the first computers. So this would be the instructions of this machine. And if you see it working, you see how the information comes into the machine, and special about a digital machine is that it can fabricate, can be reprogrammed and can fabricate over and over new patterns. And those machines are more or less still in action nowadays. Huh? So it is a kind of 3D printing because it brings together material to objects controlled by information and energy. In this case, it's a mechanical energy because you weave the threads together. In modern printing processes, it could be energy with a laser and then a UV curing material. So an entire scope of 3D printing, and that's true for all digital fabrication. There are many different approaches. And I don't believe that, for example, in future we will have one single process that can solve all the architectural challenges we have. But it will be very manifold, as diverse as architecture is. When we work with 3D printers, we don't work with the small-scale printers that you probably know from architectural offices. We work with very big machines. This is one of the biggest industrial printers. It can print sandstone. So it would bind sand particles with binder. And the print bed of this printer has already the dimension of roughly this screen here, 4 by 2 by 1 meter. But what is very specific about this fabrication process is that it has a resolution that is roughly 50 times higher than this screen. So it's 40,000 by 60,000 pixels. And this machine can print no matter what you put in as geometry in always the same amount of time. So no matter if you print just a box or a highly complex part, it will always work the same amount of time. Actually, 1.5 days for one print bed. Originally, this is developed, and that's about combining things again. That's developed for a very traditional 2,000-year-old manufacturing process, the casting process. So you can print 3D print molds and then cast metal inside. We did this here together with the students where they developed a parametric mold system for custom joints. 200 of them. They would cast the joints and then fabricate this pavilion out of it. That is, for example, now a combination of tradition and modern technology that is still up to 200 times cheaper than directly printing the joints. Students also developed this facade with the same principle, out of aluminium. So I've shown now some of the fabrication processes that will come in future and be more and more available for architecture. But it's also very important to think about the right design instruments that we have to really harvest the potential of these machines. And currently we are still using the computer in a very traditional way. We are almost using it in the same way like here on the left side. If you look at the icons of your CAD software, they are basically copies of the instruments we had on the left side. That's why we also research about new design methods. And here this is a design instrument that we developed that allows us to create forms that we could just not design with CAD software. It's based on a simple folding process, but within the computer, and folds the surface over and over. So now the architect doesn't draw and construct anymore, but he controls these parameters and defines what is the goal of the design, and the computer helps to develop that. So the computer becomes a partner in design. That is now true for these more artistic projects that we developed, but it's also true for construction. So we will have a computer that suggests new design solutions that can help us to find better solutions and maybe just extend our imagination as an architect. So here these are designs that we develop with this software. And that's also true for building design. So it's not, once you have a programmed process to develop the design, you're talking about an entire family of forms, not just a single form, but you have a family of forms. It's about how to select the best ones. So the first project that we ever 3D printed in real was this project Digital Grotesque for the Architecture Museum Centre Pompidou in Paris. Here you see the entire spatial configuration. It's called a grotto because it should show a case what happens if architecture and nature are merged together. And these are design studies that we created based on this process. But what is new when we work with computational design and 3D printing is that we can design fully in 3 dimensions. So we don't need any 2D plan anymore to draw, but also to communicate our design. Ideally, we can fabricate without adaptation. So we don't need to, for example, rationalize our design after the design process, because the machines can handle this complexity. We can also fuse structure and ornament, for example. We can have more integrated building components. Here you see the printing process in action. In this case, it's also a robot, but it's called a Cartesian robot, not just a different axis system. And the smartness of this machine is actually the print head. So it can apply binder on the loose bed of sand, and the finished projects are one-to-one printed sandstone pieces that are entirely swimming into loose sand. Nice thing about this process is that you can really print sandstone, so with the similar properties, and instead of carving the material away, you can just select and connect it wherever you need it. You can create hollow parts, you can create undercuts. This is one of the 3D printing processes that has the highest geometric freedom. You can really fabricate things that you cannot fabricate with any other method. And you can recycle the sand that you don't use. So it's also a very efficient and friendly process. You see here the installation of the 3D printed space. These are highly precise, large-scale sandstone bricks that are in the position of 1 millimeter. I'm showing this project now. It's a very radical installation. We wanted to provoke also. We wanted to show what these modern technologies can do for architecture. And architects, engineers also need to develop a sensibility of the power and of the potential of these machines. Often we treat them too carefully. These are very radical machines that introduce a paradigm change in fabrication and design. So for the first time, complexity is not a cost factor anymore. Printing this backside of the space takes as much time as printing the front side. That is really radically different. That means that we can start to design our components not only in the outside, like where we, in this case, showed the ornament, but we can also optimize on the inside. So we can reduce the thickness of these stones to 5 millimeter, where we don't need so much strength. We can also integrate spatial details like lifting details, alignment details within the 3D model and just print them. For example, this is a section of one of these stones and the data that we would send then to the printer. The layer height of this printer, although this is a 4 meter high space, the layer height was 0.2 millimeter. So it's a very precise process. And finally, the assembly of one of the most complex spaces, how it was called in media, took only 4 days. So it's like a Lego game actually on the construction site. Again, this is now a radical installation, but it shows the potential. So in future we can customize each single brick, and we can not only design the outside, but the inside, make parts hollow, and be able to integrate a lot of functional details that help the assembly on the construction site. So these are installation work that we do to learn also for real scale or large scale architecture. Just to give you another example, we now develop methods also to create more depth structures. So these are now detached from the surface with the same folding principle, completely generated by computer. So there's no more designer drawing by mouse. The computer learns how to create these shapes. In this case, it's an abstract aesthetic composition, but you can see that these porous structures could, of course, also have functional properties. They could be acoustically active. They could also help to reduce weight of components. That's what we do actually here now in our workshop together with the students. But I do think also these technologies are developing very fast. So as architects, designers, everybody who's involved in the construction industry, we have to get a sensibility of the real potential of these machines. And it's much more than we can imagine. Maybe to give you a number of the impact it can have. In these projects, we spent like almost 1 year or 2 years to develop the software, design the space, but the fabrication only took us 1 week. And that's true for all the digital fabrication process. We will have much more time as designers to design carefully, or as engineers to optimize, because we can shift the final decision of the design to a later stage in the design. So this space only took 4 days to assemble, I think 1 week to fabricate. Now, let me come to now a large-scale architectural project. So as I said, this is an installation, but it's good for learning to understand the potential. And so we collaborated on a defab house, very similar to the project that Vanderlei showed, which is under construction here now, under planning. In this case, it's a demonstrator called the defab house that should highlight the different research streams that we develop in the NCCR digital fabrication. It's not only our research, these are multiple research streams that are all integrated into a large-scale guest house at the Institute for Material Science in Switzerland. I will show you later a little bit more about the details, but in general to understand that this is not just one architect designing the house, but these are several researchers that all influence the entire design of the building. Also, we worked a lot with industrial partners, because we don't want to develop a research that has no impact on industry. We learn from industry, we collaborated deeply together, we learn from the feedback from the industry, and they are now starting to implement the research in their actual fabrication facilities. So we have a very unique site. Usually you would build a house just on a green flat land, but we build it in a kind of scaffold. This is called the nest building, which is a meter structure that is actually the only purpose from this building is to host test units. It's a very unique initiative, which is now the catalyst and driver of a lot of different research streams. Werner Sobeck also built a unit inside, Locks Group is now building a unit inside, and we built the defab house. If you look closer on this image, you see something very strange maybe for your usual experience. There's already a robot on the construction site if you look at the first level on the left side. And here close up. So this is one research stream from Composites research, where a robot would weld on the construction site a mesh that is both reinforcement and formwork for concrete. In this case, later the concrete filling is again a manual process. So it's interesting how different perspectives on the same fabrication method can help to digitalize fabrication. Here the final wall. Another process from Composites research is called smart dynamic casting. So here concrete is extruded. It's a more or less conventional process, but what is special is that you would be able to change the section while extruding. Very nice aspect of this is that the final concrete has a high, very smooth surface. Another project involved here, and I'm showing you just all the research streams that you get the picture of the diversity of digital fabrication, is robotic assembly of three-dimensional timber units. What is a big advantage of assembling three-dimensional units is that you can again have a high degree of integration. So you can install, in theory, you could install already all the cabling, all the infrastructure, just bring it on the construction site. That was also true in the defab house. So the assembly of these units took only 1 day. There's another aspect in the defab house, which is the facade. Very important, like not so much about how to heat up our buildings, but how to cool down. This is an aerogel facade. So one of the lightest materials in the world, in a loose packing between two membranes that would insulate now, and at the same time also create this kind of marble-like effect on the unit. Here the application. So let me go a bit more into detail about our part of this project, which was the slab, the ceiling system. So why is it important to think and rethink slabs in buildings? First of all, the structural mass of slabs is one of the biggest part in buildings. So horizontal elements are have much more mass than vertical columns, for example, in high rises. Secondly, it is one of the biggest visual surfaces in buildings. So usually we have a skeleton construction, and the only big visible surface is the ceiling. Lastly, it's also the place where we could distribute all the technology. It's a kind of media and infrastructure distribution platform such as slab. So we see there a lot of potential to think about this building component because we could make them more compact, more light, and entirely prefabricated. But if you talk about prefabrication and modularization, we don't think in this kind of sense. Like this is an industrial prefabrication like 100 years ago. So you would design always the same, or fabricate always the same element. You probably would extrude them and just cut them. But we think more how to design them in 3 dimensions, not in 2D, and not just standardized, but fully using digital technology. And that means we have to, also in terms of economics, think a bit different. It's not only about reducing the cost, but it could also be about increasing the functionality of these components. And in the Smart Lab, we consider the design where we would integrate acoustic performance on the surface structure, thermal activation, so to the heating, the ventilation system, and plus we want to reduce the amount of concrete needed in this lab. But the printing processes that I showed before, one challenge is to really achieve a quality that would pass all the regulations. So it's not yet fireproof. It's probably too heavy, and it has not the same strength as concrete. So what we decided is to use the 3D printing for another system. We don't use it for directly printing, but for creating the formwork. But that also makes sense, because actually formwork fabrication for concrete is one of the biggest part of the work. So I don't know if you know the engineer Nervi, for example, Italian engineer, very influential, very fantastic slabs, for example, in these buildings. He already pointed out that there are some limiting factors in concrete construction. One is actually our own minds. That's also interesting. So we can use also computers to probably overcome our own minds. But of course, it's also the formwork system, because we always work just with flat panels for formwork. And again, it's more than 40% of the cost of construction site. So if we can use 3D printing to take this out of the correlation, we can have a big impact. Let me show you a little bit what kind of design process we imagine for such a slab. So I'm showing you now some prototypes that exemplify how we imagine that the future design of these slabs would happen. So we would, for example, define the support structures, analyze the stress so we can find out where we need more material. We turn it into a geometry. We visualize it, so we test how it would look like. We send the geometry to a printer. This is the small brother of the big printer I showed. It's just 2 by 1 meter. And we would print the element. This is now the printed element within 30 minutes. So that's the actual time of the current printing technology. So to create this panel, it takes like half an hour to 3D print. It's customized, and what you could see in the sequence that there's almost no more loss of information or friction from a digital model to a real model. It is just a push of a button, literally. We can also start to optimize components fully in 3 dimensions. So you can take out the material where you don't need it. In this case, we optimized again the slab structure, because we thought, okay, how can we get rid, how can we reduce the amount of material? And in this case, with the computational optimization, we reduced over 80% of the material by just taking it out where you don't need it. The extra effect is that we also gained some voids in space where we could have the piping inside. But also, of course, we have to seriously test the structural capacity of our slab. This was the team 3 years ago. Now we don't fit anymore on one slab. You can find me somewhere on this picture. You can also find Matthias on this picture, actually. So these are prototypes where we used already the 3D printing as a formwork. In this case, also fiber reinforced concrete. Thinking about the larger construction of the defab house, we have a cantilevering situation and we have to support 2 floors, so we integrated post-tensioning. And we think about 3D printed formwork, prefabricated concrete elements, and bringing them on the construction site. Here you see the layout now of the post-tensioning cables that we use to use concrete more efficiently. And again, as I showed in the small prototypes, we develop our own design software that is able to react on the support case. In this case, it's this S-curved wall. And then can generate, we can control the rib layout, analyze the structure. We can also export the fabrication data from this software. It's a digital process, involves also different software. But what was, for example, very important in this project, the robot was responsible to construct the wall, and unfortunately it was faster than we expected, so it only needed 2 weeks. So we had to speed up our design, but also it was not very precise. So we could scan the entire construction and then directly adjust our model to the real geometry of the wall to make sure that the components fit. So just-in-time adaptation of the fabrication data. Here the rendering of the final layout. So at the end we have a combined digital formwork. For the most complex part we use 3D printing, and that's the underside, what you see here. For the upper part is a CNC laser cut timber system, because there we have prismatic geometry. So it's important to understand that here many different fabrication methods come together, but they all fit perfectly like a puzzle because of our digital model. So all the geometry, and it's really 2,000 parts for one single element, including the rebar, including the voids, the alignment pins, and all the details. But so it's a complexity that we usually only know from airplanes or so. But we could organize them all in our digital model, and they would all fit together perfectly. So it's an outlook of future prefabrication, actually. You see here the fabrication of the formwork. Again, the same printer. We would just apply binder where the formwork parts are. And of course, what you do when you 3D print formwork, you can also, again, optimize the formwork itself. So we used only 5mm thick formwork with ribs, because that is for the printer no difference. We could print them massively, but that would be too heavy. But we could just make it a very thin shell, just enough to support the concrete. These are the formwork parts. The alignment on the construction side. So prefabrication. Yeah, it's very sexy when it's glossy and there's a release agent on it. But we use two different concrete strategies. We use a fiber reinforced straight concrete, wet in wet with a casting concrete. And that allowed us to create very thin shell construction. So on most part of the structure of the slab, it's only 20mm thick, as you can see here. And the ribs itself are 10 centimeters. So also for concrete construction, pre-stressed, it's a very small amount of concrete, very minimal. We were able to also scan some prototypes, and we achieved a precision of less than 2mm tolerance for 7-meter long elements. So actually, when we had these images in our iPhone, it would identify it as airplane. So it's such a new form that AI doesn't recognize it as a slab. This is now assembly on the construction side. And these projects, and Vanderlei, you're about to start one, are also very exciting because you work with construction industry, and for example, the workers that assembled these elements, they developed a high pride to be able to assemble this very precisely. So even if it would be 1mm off, they would just readjust it to make sure that it's as precise as Swiss bottles are. We see here the interface to the wall. And we saved, that's a conventional calculation, so even there we would save 60% of material as the structure. And let me conclude maybe. So in this project we used disposable formwork because it was unique elements. But the printed formwork that we developed, the system, we can reuse it also. So it's infiltrated, the shell is hard enough, so we could use it over 20 or 50 times per element. We could save over 60% of concrete. Again, the digital model was very important to design it, but what was also interesting to follow is that within the process of the smart slab fabrication and development, printers became 2 or 3 times faster. So we have to be aware that these are technologies that are very dynamically evolving, and we basically have to predict or anticipate what will be the next steps. Just some images of the final structure. So in this case, we try to also really showcase what concrete can do once we free it from the bounds of conventional formwork. And we wanted to show also how filigree concrete can be. You see here the large-scale structure are the ribs that are visible on the surface. Small-scale structures are an ornament that showcases the resolution of the printing, but they also influence the acoustics of the space. And they, of course, influence how light is displayed on the surface. For the overall project, I wanted to show you one video here. That's at close to Zurich, the DFAB house after opening. The opening was beginning of this year, last year, no, this year. You hear Professor Kohler talking here. I don't know if you can hear him, so maybe I blend him out and talk myself. So just to show you the construction principles again, the mesh mode, robots on the construction site, welding a rebar casket, the interfaces between wall and slab. This is Peter Richner, the head of EMPA, who was responsible for the entire project. And what we talk about here in this video is also about how the interfaces between the different research teams were made possible with digital technologies. This is the Formwork Fabrication project manager of the project, Konrad Gaza. So you can imagine this project manager didn't have to work only with a single architect, but with 7 of them, so it's a challenging task. Again, the fabrication. So the DFAB house now, people who worked on this project are living inside. They can basically test. It will be there for at least 5 years. We will monitor how the structures, they are all prototypical structures, so we will monitor how they behave. We have some sensors in the concrete. We have some sensors in other parts of the building. And we can also see how people just interact with the space, so how they perceive it. And we have more than 1,000 visitors every month now. And this is really a village close to Zurich, so otherwise there would be no one going there. And that's an important aspect for us. We continue now researching and developing applications together with the industry partners involved into this project. So we all catch fire, and we came to new ideas, variations of the processes we developed, and we bring them now in the market. So whenever you are in Zurich, it's always worth a visit. You can enter it once per week. You have a free tour, so the people who live inside, they had to sign a contract that they accept visitors every week. But it's really not only this unit, there are other units that are under construction. I will show you a little bit the outlook. So after this milestone project that we developed in the last 3 years, what are the next steps? For example, we work together with the largest formwork company on dissolvable formwork. Formwork that you can 3D print and just wash away with water. We also work on, for the next unit, on bespoke stairs. So how can we use 3D printing, for example, to create unique designs of stairs that are often custom. So for example, if we want to retrofit stairs in buildings, we can use now 3D printing to really customize this. That includes also then a digital design tool for the architect. He will just design the stair and then have all the data for the fabrication ready. We developed formwork systems that reduce the amount of formwork to a minimum, just millimeter thick. So we can fabricate these concrete structures that are almost impossible with other systems. And like also the canoe here, that was a concrete canoe on a big international competition actually in Germany. We didn't won the prize for the fastest canoe, what you can see here in the face of the students. But we won the prize for the most innovative canoe. But more seriously, we also continue with slab systems. So we have a collaboration with the Philip Rock Group and the Arno Schlüter's group, where we developed a slab system, second generation, based on a follicular floor system. So we try to reduce the amount of reinforcement dramatically and integrate functional features like in this case the cooling system within the concrete element. In this prototype we use even FDM printing to create all the details. And what you see here in this prototype was exhibited at the World Economic Forum. We use only 20 millimeter of concrete, and in this case it's a concrete that doesn't require extra strength, so it's a recycled concrete. A very weak concrete actually, which has less of an environmental footprint. And can be easily recycled because we don't have a rebar system inside, it's outside of the structure. So this will be now installed in the second unit in the defab house. We also of course can design the surface quality, no matter what complexity it has. We also work on digital composites. So based on the idea, okay, what happens if one day we would be able to 3D print different materials in the same process? This is of course just a trailer of a TV show, Westworld. So they can print horses, so why can't we print buildings? But we try this with carbon fiber. For example, we print plastics and then we developed a system that we can add carbon fiber reinforcement on structures. So 3D printing doesn't need to be always a layer process. 3D printing can be also totally in space. So we can, for example, add layers of functionality with a printhead on these surfaces. Here, researcher Kwon, he also even prints conductive layers on the same surface. So 3D printing also doesn't mean that you always have a Cartesian robot. You can also print with robots, with a robotic arm with multiple axes. For example, to create lightweight structures like this chair that only weighs, I think, 5 kilo. Again, serious testing. So lastly, what I've shown many projects that would use now printing for formwork, or the sand printing that is not yet, we are also developing this further, but it's not yet the right material for construction. So what happens if we can directly 3D print concrete, and then Alain mentioned it already, the concrete extrusion or contour crafting. So we also don't believe that this will be a process that will be on construction site first, but we rather focus on prefabrication. But the advantages are obvious. I showed now even a printed formwork still requires a lot of parts and a lot of assembly. If we can print this entirely without formwork, it's even more efficient and we can be faster. We don't have any waste of the construction, and we can use the concrete exactly where we want it to be. So that allows us also to use it more efficiently. That's how our research develops. I've shown you a lot of success cases now from our perspective, but it's not always success. It requires hard research. Material doesn't always behave like we want it to be. You know better than I do. It's like a cooking process. But that's what we do in 1.5 years of research together with material scientists, with this Robert Flatt's group of physical chemistry of building materials. In the background you see already someone pumping manually. So not everything is optimized yet. But even these failures are very important for research. So we learn, we will even discover some aesthetic beauty in this practice. So after 1 year, the progress is, that's also nice and it's very visible. So we can now print higher structures because the concrete, better foundation, still some manual labor. But we can, for example, also not only print in layers, we can now align the layers so we can orientate the concrete contours in a more efficient way. So we can print higher now. As I told you at the beginning, our robotic fabrication lab is actually the biggest 3D printer in the world. So we can print, in theory, 40-meter long pieces. Of course, we have to change there a little bit we have to have an entire concrete factory in the background then. So we developed, for example, something for the out-of-concrete extrusion with our MRS students, so the postgraduate students. And they had the unique opportunity to develop something. Now I'm showing for the first time pictures of Switzerland, actually. That's our environment where we are working. A valley 2 hours away from Zurich, where we developed a stage out of concrete columns. And here you see the documentation of this. It's a cultural festival, and they are seeking for innovative ideas to combine actually culture and construction and engineering. This is also a region of Switzerland where not so many people are living anymore, so it brings in some new life by showing a little bit outlook of the future. So students do exactly what I was talking at the beginning. It's a digital process chain. They develop their own design software, which even integrates the fabrication path, and then send the data to the printer to fabricate within 2 hours concrete column. 2.5 hours. I mean, you experienced the fabrication, so of course not every column was a success. So here, an image of the final exhibition. It's still there. It will also be exhibited at the World Economic Forum, maybe without the dancers. We also create a post-tension column, and here maybe just to give you the numbers again. So we could reduce the weight of the column because it's hollow to 400 kilo, which is very light for a 3-meter concrete column. And there was really less than 2 hours print time. So let me end with a quote from Henri van der Velde, an architect from the last century. It's about to chase our dream of a smooth material which can follow our ideas as easily as the language follows our thoughts. Thank you.
Good morning. Congratulations. It was amazing. Do you think it's possible to use casting steel instead of casting concrete, using the same technology to build the same structure?
Let me maybe rephrase the question if I understood it right. So you were asking if instead of casting concrete, to cast steel or to 3D print steel, or
using the same technology but using casting steel instead of casting concrete to build the same structures. I mean the slabs and the columns and so on.
Yeah. So on one side, some of the technologies are showed. For example, the binder jet printing of the formwork for the concrete, that is even originally developed for casting metal. So that could be possible. But I would say that each material, and there's a lot of research going on in digital fabrication of steel and also 3D printing in contours, for example. But I think the design would always look different depending on what kind of material you use. So you could definitely do entirely different design. We've seen the 3D printed bridge, for example, from metal. I think it would not be right to just do exactly the same out of metal, but you would then also have to redesign the entire system. But in general, it's also an exciting topic how to combine metal with concrete in the same digital fabrication process, so we could really solve the reinforcement challenge, for example. Don't know if this was the question. Thank you.
Next. More questions? I think everyone is in shock. Well,
What have changed in the concrete composition that allow to do work?
So I'm not a material scientist, so I can just explain you from my architect's perspective and what I learned doing this interdisciplinary project. But it's critical that the concrete develops enough strength to support the upcoming layers. If it would not, then it would collapse, as you could see. Now, how can we control the speed of developing strength of concrete? We can add an accelerator, for example. And Robert Flatt group, for example, developed a formulation where they can really say within the next 15 minutes the concrete will become hard enough to support the next layers. It's a process that has very different parameters. So it depends also, of course, on how big is the object that you're printing, because that means that you need more time to come back to the same layer. So the bigger the object you're printing, the easier it is, because you don't need accelerator because it might take a minute until you're in the same position again. But when you print just the column, you need to accelerate fast. But one can control this very precisely. It's also just a small amount of chemical mixture that you add inside to speed up the process. Requires a lot of calibration, but I think, for example, Raphael can give you more insight on that. If you accelerate it too fast, you don't get it out of the pump anymore. It's also a drama. Also true. Yeah, that's on the other side. If it's too fast, then it's loose layers that are not connected. You have to find the sweet spot that makes it also so exciting. And I think in general, digital technologies, including sensors and a calibration system and smart software that can react on this, only allows such a complex process actually that is so sensitive.
Other question? No?
One more question. Well, sorry for my English, I'm a little bit rusty, but I love architecture and engineering, and I'm from Brazil. It's a city from middle central of our country, and there we use traditional methodology to construct and build some a lot of buildings. So this method is the same for small buildings and skyscrapers, for example. It's really important this kind of research and all of what you are doing in this moment. So, how is your vision for this technology in our country here in Brazil, especially in our area, in our region?
It's a good question.
Do you understand?
I understand, but I can also repeat if I understand well. So, I showed now technologies that are maybe globally developing, but what is specifically interesting for your country or your situation for the future development of these technologies, and what is my vision on that? Huh?
Yeah.
And I do think, of course, there are some points that I mentioned before. Huh? So this is a global responsibility that we have. We need to reduce the amount of concrete or cement that we are using. And in a country where there's, for good reason, also so much use of concrete, it can have a high impact. So the sustainability, to increase that, it can be a big goal to achieve. But at the same time, we also have to make sure that this is affordable even in future. Currently, I guess there are construction methods that are cheaper because maybe labor is also cheaper, but also here it will develop further. And so in order to be able to create affordable housing, we also have to really invest in research in digital technologies. And last but not least, I think it can maybe help us to also develop really a rich, diverse built environment, so that we don't need to work on standard. So currently we have to always make a compromise. Do we want to have it rational, so cheap and fast, or should we make it beautiful? And I think both aspects are important, and the digital technologies can help to bridge both together.
How is steel in all this process? Because you told about concrete, everything about concrete, and the steel. Where is the steel?
Yeah. I mean, the steel in our project, the steel was highly important. So some people would say that it's basically a steel construction because we took away so much concrete from the slab. So at the end, we only have 20 millimeter or 25 millimeter cover, and there's a steel basket inside. Interestingly, you also use CNC bending for the rebar. But on the bigger picture, I don't think that we should put all our potential research in one material. I think we have to learn to use each material most efficiently, and the way how digitization kicks in, for example, concrete construction, timber construction, steel construction, will have a different speed, but it has to happen in all of the disciplines.
Marnie, what kind of license apply technology to develop? Is the data open to the public?
Different models. Some research we do together with industry, and then depends on the contract with the industry partner if the know-how can be all published or not. But our favorite model is actually to do open research, and of course we publish then the results. So the findings are, if we are not bound by any agreement with the industry partner, we would publish the results. And we would also publish the software development or the formulation. So we want actually everybody to learn from that. We also learn from previous research. I think it's very important to further develop that. It's basically the open source idea, but also on hardware development. For example, we have one researcher on our team that develops a binder jet printer. The printer that I showed at the beginning, it's an industrial product and it's very difficult to change, to test other materials. But we have one researcher, for example, who develops his own system, which is just very good for testing materials. And this we will publish online as a kind of starter kit that everybody can use this for testing different materials.
Have you tried to use gypsum as a binder? Because gypsum in construction is used a lot in the vertical way.
Good idea. We just haven't done that yet. No? That's thank you. So we try that. No, but it's of course makes sense. The materials we are using currently materials is a big challenge of the entire fabrication line. So we are always thankful and looking around for new materials. But gypsum was not yet on our radar, or I think there are some gypsum printers, but they are actually binding the gypsum even with resin. So it's not a real gypsum that you create at the end. But that would be, for example, a good choice. We also look into clay. We look into geopolymer. So it's another could also be replacing a little bit of the semester. Yeah. That is an important aspect, and in the projects that I've shown, it's different. So it's not always the same. In the exhibition project, the form finding was very radical, done by the computer, and it was like a growing process where the architect's role would be to just steer a little bit the direction of the form development. We also used the computer there to optimize the structure, but that was after the design. So it's probably then not a form, it's a form finding, but not finding form for structural reasons. But after the form was found, we also use a computer to rationalize it to, at the end, still optimize the fabrication process. Using less material, making the details nice, and try to hide the seams. I don't know if it was so successful. But that was then a post-rationalization, which I think is also very valid. Because, for example, we developed a system, not public yet or so, but where we could basically create the formwork or the inner structure for almost any shape. And that will also be then very helpful. Ideally, you integrate this already earlier in the design. And in the slab system, we also work together with the structural engineer, Josef Schwarz. And we had even conceptual discussions about the overall system that we want to use, like in terms of ribs and post-tensioning. So that was really, I think this will also stay in the human decision part, that you have to think, okay, is this now, are we using post-tensioning, or are we creating a funicular floor? And then we use the computer to find, for example, to adjust an optimal layout of the ribs. So it's not always dominant, and the importance of the structural aspects depend on the project, I think. And I think that's also true for architecture.
There is more people trying to ask questions. He will be here. We have coffee break now. They are Swiss. We have to be on time, so stand early. That's it. And after the break, we are going to come back. We have two presentations in the morning. Thank you very much.